Today we are going to talk about a new way to measure angles. Last week I mentioned that we wanted to make sure our calculators were in degree mode before we did any of our trigonometric calculations. Otherwise we would get a wrong answer. When you went in and verified that that was the case, you may have seen radians as an option, or even gradients. Well, today we'll talk about radians. In this class, we won't worry about gradients. We'll just worry about degrees and radians. And you will need to, from now on, always be checking to make sure that your calculator is in the right mode before you do any calculations. Otherwise, you will get the wrong answer. It's kind of frustrating at times when that happens, but I've run into that more than once myself. So let's take a look at a circle here that I've drawn on a coordinate system, and I'm going to say that the radius of this circle is 1. And if that's the case, then we have certain things about this circle that will make it easier for us to calculate. For example, the circumference of a circle, which is the distance around the outside edge, because it's not really an edge, but the distance around the outside of the circle is equal to pi times the diameter. And the diameter is twice the radius. So we could also say that that is 2 times pi times r, which is going to help us now because we know what r equals. And so if I replace r in this equation with 1, which is what we have for this particular circle, so we've got 2 times pi times 1, and now we know that the circumference of this circle is 2 pi. So the distance around this circle is 2 pi. That means if we start, as we did last week, with our angle here start on the positive x-axis and rotate around counterclockwise, then we would start at 0. And after rotating 1 full revolution around the circle, we would be at a distance of 2 pi. And now let's extrapolate on that idea just a bit. So if it's 2 pi for 1 full revolution, then that means half a revolution would be pi. Just dividing that 2 pi by 2. And now let's kind of break this down a bit more. Half of pi, meaning now up here at the positive y-axis, rotating half of, let's see, if full pi rotates to there, half of that would take us to the positive y-axis, and half of pi is simply pi divided by 2. So that's how far we've rotated around the circle to get from the positive x to the positive y-axis. If we're rotating counterclockwise, we've rotated a distance of pi over 2. And of course, rotating all the way around to the negative x-axis, we've already said is pi. Well, let's suppose we rotate to the negative y-axis. Well, if each quarter of this circle is pi over 2, we could just kind of add those up. We've got 1 pi over 2, 2 pi over 2. Well, this one down here must be 3 pi over 2. So that would be our distance around to the negative y-axis, is 3 pi over 2, and continue on, and we've got 2 pi once we get to the positive x-axis. So we can really break this circle down as much as we want like this into versions or relationships with pi, recognizing that pi was halfway around the circle. And one of the things that we will often populate is a figure called the unit circle. And that's actually kind of what we have here. This is a unit circle, because r equals 1, and unity is 1. And so by saying that r equals 1, we've called this a unit circle. And now we just need to kind of figure out what all the pieces are on this circle. Now we could break this down even further. Maybe we go here halfway between the positive x-axis and the positive y-axis. Well, that would be half of pi over 2. And so we could take that pi over 2 and multiply it by 1/2. When you multiply fractions, you multiply the numerators together. Pi times 1 is pi, and 2 times 2 is 4. So we could say that halfway through was pi over 4. Now, we can also kind of use that to add up. So another pi over 4, 2 times pi over 4 is pi over 2. 3 times pi over 4 takes us over to this halfway point. 3 times pi over 4 is simply 3 pi over 4. 4 times pi over 4 is simply pi. And then we'd have another one over here in the third quadrant. That would be 5 times pi over 4. And then one more would be 6 pi over 4. Now let's see how that simplifies. 6 pi over 4, if we divided the 6 by 2 and the 4 by 2, we would get our 3 pi over 2. So that simplifies just fine. We've got another quadrant divider over here in the fourth quadrant. So if we've gone 6 pi over 4, now let's go one more to 7 pi over 4. And then we could go one more to 8 pi over 4. And 8 divided by 4 is simply 2. We're back to 2 pi. So you see that once we divide these into sections, we can continually divide. We can divide it into even smaller sections, or we can just add up the sections we know, get some of these other ones that maybe we haven't worked with yet. And that can really help. As a matter of fact, you have a figure in course documents of a unit circle. And I want to bring that up now. We've got one there that's completed and one that is empty. And so let's take a look at this one that is empty. You have a copy of this on course documents, like I said. And if you want to have an empty copy with you for an exam, you may. You will have to show it to the camera before you start to prove it's empty. But you may have it, though I'll show you a trick in a bit that makes it so you don't really even need a copy at all. Remember, I wanted you to memorize those 2 triangles, and we are going to use those to help populate this unit circle quite a bit. Notice we have a lot of symbols here. Let me take a look at just a section of this right here. And I'll break that out a bit. We have a line with a degree symbol, comma, and then a line up here. Then we've got what is clearly an ordered pair beneath that. Okay, so what we will do is we will put the degree measure in this box. And then we will put the radian measure next to that. And down here, this is the XY coordinate of the point at the end of that radius. And so we will use that to determine a lot of features for sine, cosine, and tangent, and so on. So let's go ahead and populate this unit circle a bit. First, we'll start with degrees. That just kind of go back to what we learned last week. Here we had 0 degrees. We rotated up to 90 degrees, over to 180. That was a full circle, half circle, or a straight line. Keep going, and we had 270 degrees over here, and then we continued up, and we had 360 as one full circle. Now in this first quadrant, say we divide the 90 by 2, that gives us 45 degrees. Let's just worry about that quadrant divider. I should say quadrant bisector, since the others divide as well, but that's 45 degrees. We've got our 90. We have a bisector in the second quadrant that's 45 degrees more than the 90. So that would be 135. Another 45 takes us to 180. Another 45 takes us to 225. Another 45 takes us to 270. Another 45 takes us to 315. And a final 45 brings us up to the 360. That works pretty well. Now let's notice we've got 2 other lines here in the first quadrant. Those are our 30-degree angle and our 60-degree angle. And remember, these are angles measured from the positive x-axis, our initial side. That's the measure of that angle to that terminal side. So that's really what we're talking about when we put these degree measures on there. Well, notice that 2 30s is a 60. Another 30 takes you to 90. Another 30 takes you to 120. Another 30 takes you to 150. Another 30 takes you to 180. Another 30 takes you to 210. Another 30 takes us to 240. Another 30 to 270. Another one to 300. Another one to 330. And our final one takes us back up to 360. So we used those 30-degree measures to populate all of the other angles in degrees. Now we could have used the 60 to get some of those. We've got 60, add 60 to that, gives me the 120. Add another 60, gives me 180. Another 60 gives me the 240. Plus 60 is 300. Plus 60 is 360. So you can see how these all add up and help us populate that particular portion of the unit circle. So now let's jump to radians, which we started talking about today. I'm going to use the blue for that. We've got 0 radians here at the positive x-axis. We said we had pi radians over at the 180-degree or negative x-axis. We divided that by 2. Pi divided by 2 is pi halves, and this is where that fraction bar comes in. Just gives you that you can use to create the fraction, because most of these will be fractions. We also said that the 270 degrees, the negative y-axis, was 3 pi over 2. We said that 45 degrees was half of pi over 2, or pi over 4. And then we populated all of those. So we had 1 pi over 4, 2 pi over 4 would be the 90 degrees. 3 pi over 4 was what we came up with over here in the second quadrant. 4 pi over 4 just equals pi, so now we're at the negative x-axis. 5 pi over 4 takes us down into the third quadrant. 6 pi over 4 we showed would simplify to 3 pi over 2. And 7 pi over 4 was that bisector in the fourth quadrant. 8 pi over 4 was back up to 2 pi. So remember that 2 pi is also one full circle. So let's look at some of the others that we haven't populated yet. 30 degrees, for example. How many 30s fit into 180? Well, let's divide that. 180 divided by 30. One cool thing with zeros is you can just cancel those. It's like dividing top and bottom by 10. And so we've got 18 divided by 3, which is 6. So 30 degrees is 1/6 of 180. Well, remember 180 degrees is also pi. So let's say, well, then 30 degrees must equal pi divided by 6. And now we'll just follow our way around the circle here, just like we did with our internal arrows here. Add one more pi over 6, and this would be 2 pi over 6. But that simplifies to pi over 3. We could have done the same thing that we did with 30 degrees and divide 180 by 60. Cross those zeros out. 18 divided by 6 is 3, and you can see that pi over 3 would be 60 degrees. But we're looking at the 30s right now. So we had 1 pi over 6, 2 pi over 6, 3 pi over 6 is pi over 2. 4 pi over 6 would simplify to 2 pi over 3. And then we'd have 5 pi over 6, which won't simplify at all. 6 pi over 6, which simplifies to just pi. That's 7 pi over 6. We've got 8 pi over 6, which would simplify to 4 pi over 3. 9 pi over 6, which would simplify to 3 pi over 2. 10 pi over 6, which would simplify to 5 pi over 3. And then we've got 11 pi over 6 and 12 pi over 6, which would simplify to simply 2 pi. So you can see, again, by dividing this into sections and then adding those sections together, we can populate all of the radian measures we have here. Now that can be really quite useful. We have relationships between degrees and radians now. Where did this idea of radian, or this word radian, come from? It comes from the radius, actually. So if we are to say, take a radius, that would be right here, and then bring that up to move it around the outside edge. Oh, I don't want a line because I can't curve the straight line quite as well. But if I were to bring that up here and rotate it around the outside edge, it would bring me up to about there. That would be one radius's length along the outside edge of my circle. That would be the measure of the angle created there is 1 radian. And if we put a second one down, as it turns out, this is about 57 degrees. So we put a couple of those, takes us over to about 114. That would be 2 radians. 3 radians would be right about here, which is kind of cool since pi is about 3.14. So about 3.14 radians to get halfway around the circle. Twice that would be 6.28. So little less than that. Maybe this would be 6 radians. So you can see that this will divide into a little over 6 radians. And that also highlights why we really need to be careful with the units in our calculator. Because if I try to take the sine of 30 degrees, for example, but I'm in radians. Now I've done the sine of 30 radians. And if once around the circle is a little over 6, 30 radians would be almost 5 full circles. And that's clearly not what we're talking about when we're talking about 30 degrees. So we really need to be careful there with our units in our calculator when we're plugging those in. So we've got a nice relationship here. Let's see. Undo some of this radian stuff on the outside. I think that might be a little distracting. But let's look at one relationship in particular, and that's this one here, where 180 degrees is equal to pi radians. That means that 1 would be 180 degrees over pi, which would equal pi over 180 degrees. Those all equal 1. So I'm going to take advantage of that so that I can convert from one to another. Say I've got 120 degrees, and I want the equivalent in radians. Well, what I'm going to do is I'm going to multiply this by 1. I am going to multiply by a very particular version of 1. And I am going to multiply by that version so that now my units cancel. Degrees divided by degrees would be unitless. And now I have just radians left. So I've got 120 pi divided by 180. Well, as we said before, when you end in zeros, you can cross those out. And now 6 goes into each of those. 6 goes into 12 twice. Still have pi. 6 goes into 18 thrice, or 3 times, and I end up with 2 pi over 3. And sure enough, 120 degrees is 2 pi over 3, just like we saw earlier with our adding of unit portions. So we can always do this conversion. If I ever get a little confused, or it's an angle that's not on this unit circle, I can do a conversion like that. We can go the other direction. Say I've got 3 pi over 4 radians. How many degrees is that? Well, I'm going to multiply that by 1. And the one I'm going to use is 180 degrees over pi. And the reason I use that one is so that the pi in the numerator here will cancel with the pi in the denominator there. Anytime I can do a cancellation like that, it will ease my work. So now I've simply got 3 times 180, which is 540. Still have degrees. Divide that by 4 times 1, which is 4. 540 divided by 4 is 1, let's see, 35. We still have the degree measure. So 3 pi over 4 is 135, and that's exactly what we found when we were looking at our work before. So having that conversion from degrees to radians or radians to degrees will really help. And the key to tell you which of these two you will use is thinking about, what do I need to cancel? What do I have? If I have degrees, then I need to have degrees in the denominator so they cancel. If I have radians, I need to have radians in the denominator so they will cancel. It's a simple unit or dimensional analysis like we learned in algebra, and it's incredibly powerful. I was talking with a former student yesterday who is in the engineering program at Boise State, and he was telling me how powerful unit conversions were for him this semester and how he finally realized their power as he was going through his fluid mechanics class. It just really helps a lot to watch those units. You will make very few mistakes once you can start watching those units. So that's our unit circle. Now we'll populate those ordered pairs in a bit. For now, let's leave the unit circle for it. Let me hide that so it's not in the way too much. Okay, so back to our original circle here. We had 1 radian measure. It was a little less than 60 degrees. We still have r equal to 1. And so this distance around the outside, which they call s, that's the arc length, also equals 1 because we took the radius and we laid it down around the outside edge. So that distance is exactly the same. And I told you that this angle measure here, which I'm going to call theta, is 1 radian. And there's actually a really good relationship here between r, s, and theta. The way I remember it is s equals r theta. In the book, they've got that theta equals s over r. Clearly, those are the same thing. It's just different ways to write it. For me, it's easier to remember that s equals r theta. But regardless, which one of these you use, theta must be in radians for this to be true. But that relationship can really help us. Now we can get some understanding about how circles are related to each other. Say we had a circle that was a little bit bigger, such that the radius was 2. So now to get all the way around to here, if we had r equals 2, then that means we must have an s that equals 2, but we still only have 1 radian is the angle measure. So you can see how those are proportional to each other. So the size of the circle will affect the length of the arc that's on the outside edge when you are turning through an angle of 1 radian. Another way this can really help us is when we are looking at angular velocity or angular speed. Now, when I talk about that, it's how fast something is spinning. And we've got a lot of circles that spin in our world, and understanding how fast they spin can be really useful. Velocity is simply a distance divided by time. We know that. How fast did you go? I went 30 miles per hour. Miles is a distance, hour is time, miles per means divide. So miles per hour makes complete sense. We're totally used to that. And that gives you your, what we usually call speed. So we've got I mentioned when we were talking about our Greek letters that we would use omega. This is our angular velocity or angular speed. And this is, well, how fast is it spinning? So how much of an angle does it go through in a given time? So this would be radians per second, maybe. So I'm just going to go ahead and call this speed. I know I used a v for velocity. I'm just really used to that. This would be angular speed. And so now we can find a relationship between these two. Notice that s equals r theta. So maybe I can replace the s here with r theta. That makes sense. So v equals r theta over t. Well, it's also true that theta over t is omega. So I could write this as r times theta over t. Those equal the exact same thing. And if theta over t is omega, then V equals, and I always remember it, omega R. R omega works just as well. So your linear speed equals your angular speed times the radius. And that can be really useful for us. Think of it this way. If you've got a wheel and you want to go forward at a particular speed, how fast does that wheel have to turn to give you that forward speed? Well, that depends on the radius of your circle. If you've got a really small wheel, it's going to have to spin a lot faster to move you a particular speed forward than a large wheel does. That large wheel can rotate once and get you, let's say, once in a second, and that will get you its circumference forward. The smaller wheel, if it rotates once, gives you one circumference forward. So if you want to get the same distance as the larger one, you're going to have to go through several circumferences to get to that distance. So we'll use this relationship that V equals omega R to figure out how fast something has to be spinning to give you a forward velocity. Let's take a look at a particular problem that will allow us to calculate. We've got this one. We've got a Toyota FJ Cruiser traveling at a speed of 70 miles per hour. Its tires have an outside diameter of 30.875 inches. Find the angle through which a tire turns in 10 seconds. So we're given quite a bit of information here. Let's see what we have that will help us. 10 seconds, that's a time. The truck is moving, or the vehicle is moving forward at 70 miles per hour. That's a velocity. We have a diameter, so that's d, which equals 2 times the radius. So we've got all of those set up. We need to find the angle that would be theta. Okay, we know that V equals omega R, and that omega equals theta over t. So we could say that V equals R theta divided by t, just replacing the omega with theta over t. Well, we've got V, we've got t, we've got twice R. We ought to be able to find theta pretty easily. We do have a problem here, though, and that's our units. Remember I said we really need to watch our units? Well, let's get these all into the same units. So our diameter, which is twice R, so that means that R equals diameter divided by 2. Well, our diameter is 30.875 inches. I'm going to divide that by 2 because I want the radius, not the diameter. And now let's convert from inches to feet. I know there are 12 inches in 1 foot. Notice that this equals 1. And I do that on purpose. I'm just multiplying by versions of 1 so that my units will cancel. So now I have inches in the numerator and inches in the denominator. Those will cancel. I'm left with just feet. When you do dimensional analysis this way, you multiply the numbers on the top and you divide by the numbers on the bottom. So 30.875 times 1 times 1 is 30.875. Divide by 2, divide by 12 is the same thing as dividing by 24. And our final units are feet. So go to my calculator and I'll type in 30.875 divided by 24, and I get 1.29 feet. Now let's convert our miles per hour. We have 70 miles in 1 hour. We know that 1 mile has 5,280 feet in it. So now the miles will cancel, and I'm left with feet per hour. Well, I know that 1 hour is, because we're only looking at 10 seconds, let's go ahead and convert to seconds. 3,600 seconds in an hour. Oh, you know what? Let's say I didn't know that. I know that 1 hour, though, is 60 minutes. And I know that 1 minute is 60 seconds. So now the minutes will cancel, the hours will cancel. I'm left with feet per second. And so I've got 70 times 5,280 times 1 doesn't really do much to me. Divide by 60, divide by 60. And when I do that in my calculator, 70 times 5,280, divide by 60, divide by 60, I get 102.67. And now my units, the ones that aren't crossed out, are feet. Oops, sorry about that. Feet, and in the denominator I have seconds, so feet per second. That's the velocity. And up here we were calculating radius. So I've got V, R, I've got T. Let's plug all of that in. 102.67 equals R, which is 1.29 times theta divided by the time, which is 10. And now I just need to solve for theta. Well, if I multiply by 10 divided by 1.29 on both sides, anything I do to the left, I do to the right, correct? So now these 10s will cancel, the 1.29 will cancel. And when I say cancel, I really mean I end up with 1, because 1.29 divided by 1.29 is 1. 10 divided by 10 is 1. And 1 times theta is theta. And now I've got 102.67 times 10 divided by 1.29, and I end up with 795.89, which is about 796. And this is our angle, so that would be radians. That is the angle through which that tire turns in 10 seconds when you're going 70 miles per hour down the road. Pretty interesting calculation there. You can figure out how many times around the circle that is by dividing that by 2 pi. 796 divided by 2 pi is 126.7. So it rotates 126.5 times in 10 seconds. Now you can perhaps look at the wear on the tire and how things are affected that way. If you were to become an engineer, you might use these calculations to build a better tire. Lots of benefits we can have there. Really handy. Another sort of problem we might run into is something like this, where we have 2 gears that are meshed together. One gear wheel turns another, and the wheels have a 9-inch and a 5-inch radius. The smaller wheel rotates at 48 RPMs, or revolutions per minute. What is the angular speed of the larger wheel in radians per second? So we've got this small one rotating around at 48 RPMs. Notice if that one's rotating that way, this one must rotate this way, otherwise the teeth will grind. We don't like that too much. So let's see some benefits here. Maybe omega, we've got V equals omega R. but omega is in radians per second. And we've got rotations or revolutions per minute. So maybe we need a conversion there. We know that 1 revolution is 2 pi radians. And we know that 1 minute is 60 seconds. So the minutes will cancel. I'm left with radians per second. So 48 times 2 pi divided by 60. That gives me 5.03 radians per second. And that makes sense to do that conversion because I want omega in this calculation. And omega is, recall, theta over t. Theta is radians, t is time, so radians per second. Also notice that right here where the teeth mesh, the velocity, vertical velocity has to be the same for the small wheel as it is for the larger wheel. If the smaller wheel is turning faster than the larger wheel, the gears will strip. You can't have that. So if the velocity of the same, velocity of the little is equal to the velocity of the larger, v1 equals v2, then that means omega 1 times the radius of 1 equals omega 2 r2 e2. Okay, so we've got the radius here. We've got omega. Oh, I probably should have written that differently. We've got omega. We just simplified that over there. 5.03 times the radius of 5 equals omega times radius. Well, now all we're missing is omega 1 in this calculation. That's what we're looking for. The angular speed of the larger wheel in radians per second. So we've got 5.03 times 5 divided by 9 gives us that angular speed, and that would come out to be about 2.79 radians per second. Handy calculation, this relationship between v, linear speed, and angular speed, omega, and it's based on that radius. And that's how they wrapped up 6.4 in our book. You'll find that 6.5 is a lot about the unit circle. So what we've talked about already will help us a fair bit with that. But I do want to extend just a little bit more our discussion of the unit circle. Let's see if we can't get those ordered pairs. All right, so this is 30 degrees, 45 degrees, 60 degrees, 90 degrees. This was 0 degrees. We had 0 radians. This was pi over 6. This was pi over 4. This was pi over 3. And this was pi over 2. We had all of those angle measures. Well, let's do something here. Let's drop a vertical from our 30-degree measure down to the x-axis. And now we have a right triangle. It's actually a 30, 60, 90 right triangle. So our relationship of sides is 1, 2, root 3. We'll just take a look at this for a minute. We've got an x value and a y value that get us up to the point at the end of the terminal side. Remember, I told you that ordered pair is the ordered pair for that terminal side. So we have a relationship here of, oh, you know what? We said this was a unit circle. That's going to change things a bit. Our radius can't be 2. Our radius needs to be 1. So I'm going to divide that by 2. If I divide that by 2, I need to divide the other sides by 2 to make this work. Now my radius is 1. Now it's the unit circle. Now my y value, I'm going to rewrite it over here so I've got a little more space. My y value is 1/2. My x value is √3/2. That's the ordered pair at the end of that particular ray. Now, let's take a look at this just a bit. If sine of 30 degrees is opposite, which is the y, over the hypotenuse, which is r, and r equals 1, that means our y value is the sine of 30. 1/2 is the sine of 30 degrees. Plug that into your calculator, sine of 30 degrees, you'll get 1/2. If we used our original triangle there, we had 1, 2, √3, 30-degree angle. Sine is opposite over hypotenuse, which is 1/2. Cosine of the angle, I'm just going to use theta now in case we decide to go to the 45 and 60, is the x value over the radius, adjacent over hypotenuse. If the radius is 1, then it's x over 1, so x would be the cosine. So the cosine of 30 degrees is √3/2, and if we go over here to our triangle, adjacent is √3 over a hypotenuse of 2, √3/2. So what we have here is the cosine of our angle and the sine of our angle. That's how we can populate that ordered pair. First ordinate will be the cosine. Well, it's the abscissa, but the x value will be the cosine. The y value will be the sine on the unit circle. Now think about this. We have already said that the ratio of sides is dependent on the side of the angle. So even if we have a circle whose radius is 2, the ratio of sides will still work out and give us the same √3/2 for 30 degrees. All right, now I'm going to take that idea and I'm going to help populate this unit circle. So let me hide what I have on there. We'll do a little bit more here. Again, we have 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90. We'll have our 2 triangles, just for reference. We had the 30, 60, 90 and the 45, 45, 90. And the ordered pair is cosine of the angle, sine of the angle. So let's see what we have here. The 0, now we know that point. We've moved 1 along the x-axis and 0 on the y. So that's the point 1, 0. Well, now we know the cosine of 0 degrees. It's 1. The sine of 0 degrees is 0, reading it off of that ordered pair. The ordered pair straight up here, we've moved up the y-axis. That would be 0 along the x and 1 along the y. So that tells us the cosine of 90 degrees is 0 and the sine of 90 degrees is 1. Well, let's populate these others. Now I'm going to use the triangles to do that. But for 30 degrees, the sine of 30 degrees is opposite over hypotenuse. So that's 1/2. The sine is 1/2. The cosine is √3/2. Now we've got that ordered pair. For 60 degrees, the cosine is 1/2. The sine is √3/2. For 45 degrees, both sine and cosine are 1/√2, which we would rationalize to √2/2. We've already talked about that in our previous video. So now we have the ordered pairs for all of those in the first quadrant. That's covered. Let's extend over into the other quadrants where we had 180 degrees. And I'm just going to deal with degrees right now instead of radians. But the same would be true for radians. The sine of pi/4 radians is √2/2. The sine of pi/6 radians, which equals 30 degrees, is 1/2. So that all works. Here we had 120 degrees, 135. We have, let's see, 150, 210, 225, 240, 270 down here, 300, 315, and 330. All right, the ordered pair over here at the 180 degrees, again, back to our coordinate system, our Cartesian coordinate system, we've moved -1 on the x-axis and 0 on the y. So that also tells us our cosine of 180 is -1, the sine is 0. Down here at 270 degrees along the negative y-axis, we've moved 0 on the x and -1 on the y. So now we know cosine and sine of 270. All right, now I'm going to take us back to algebra when we were talking about symmetry. We found that when we had points that were symmetric about a particular axis, all we had to do was change the sign of either the x or the y. So let's look at the point up here at the end of 120 degrees. Well, that is at the same y level as 60 degrees. So the y would be identical, √3/2. The x, however, is on the other side of the y-axis. It's the negative version. So that would be -1/2. We can do the same thing with the 135. It's at the exact same y, but it's got a -x. 150 is relative to the 30, has the exact same y, but a -x. Notice, remember back when we were looking at the quadrants, we said that all students throw chalk. And now this perhaps makes even a little more sense. Sine are the y values. Well, y is positive above the x-axis, so the first and second quadrants will have a positive y value. And if the y value is the sine of that angle, then the sine is positive. Cosine is the x value, whereas cosine negative, well, that's to the left of the y-axis, so we'll have negative x values in the second and third quadrant, so cosine will be negative there. Cosine is positive to the right of the y-axis. So we'll have positive x values in the first and fourth quadrants, positive cosines. So it all works out that way, and this reflection helps us. Now we could take that 150 that we just did, and we're going to reflect across the x-axis, which means our x value is the same. -√3/2. Our y value now becomes the negative version of what we had before, so -1/2. 225 is reflected from 135. So the same x value, -√2/2, and now we have a negative version of the y, -√2/2. 240 is the vertical reflection of 120, or reflecting it about the x-axis. So we'll keep the same x, and we'll negate the y. And we already knew in the third quadrant, both x and y were negative. Now we know the sine and cosine of all of those angles on the unit circle in that quadrant. Again, all the x values are positive over here in the fourth quadrant, and those are reflections of the angles in the first quadrant. So they'll keep the same x values, 1/2, root 2 over 2, and root 3 over 2. Their y values will become negative versions of those in the first quadrant. And now we've fully populated the unit circle. We know the ordered pairs, which tell us cosine and sine for all of those angles in all of those quadrants. And that is really handy, in my opinion. Now I'm going to show you a little trick that might help you, because we all actually kind of carry the unit circle with us as long as we have all 5 fingers on our left hand. So there's a left hand. Hold it up, palm facing you, and you can see you've got those fingers. Now, if we were to try to join a club, they might say, you know what, come sign up. Use that phrase. Sign up. And we will take our position here, and we'll take the square root of the position and divide it by 2. This is when we're moving up, position 0, 1, 2, 3, and 4. So we'll take the square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2. Well, the square root of 0 is 0. Divide that by 2 is 0. Square root of 1 is 1. Divide that by 2 is 1/2. Square root of 2 is the square root of 2. Divide by 2 and you have that fraction. Square root of 3 over 2 follows that same bit. Square root of 4 is 2. Divided by 2 is 1. And notice those are the sine values for all of these angles in the first quadrant. You sign up. Well, if you sign up, that must mean that you cosine down. Let's see. But we'll do the same thing, only now the positions change so that 0 is our thumb. So we end up with, let's see, I need some room here. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2. And sure enough, those are the x values of all of these ordered pairs. So your left hand is the unit circle in the first quadrant. If you remember, you sign up for stuff. And you start at position 0 and work your way up to 4. You don't have to memorize that. I think it's useful, but you don't have to memorize it. I think those 2 triangles that we started this whole thing with, those give us all that we need and cover that first quadrant. Then you can easily just use symmetry and look at the other side of the axes, see that you have the same x and y values, but they're either positive or negative. That'll cover it. But regardless, now we know the sine cosine of all of these angles on the unit circle in degrees or radians. And so that's going to help us just immensely throughout this section. So if I wanted, say, the cosine of 3 pi over 4. Let's come over here. 3 pi over 4. This was 1 pi over, I need better color. 1 pi over 4, 2 pi over 4, 3 pi over 4 is over here. I know we didn't populate that before. So what is the sine? Well, that's the y value. So the sine of 3 pi over 4, I just read it right off the unit circle, is root 2 over 2. The cosine of 3 pi over 4 is the x value. That would be a negative root 2 over 2. Just like that. Tangent is, oh, let's take a look at that. Oh, you know what? I should go back to the last layer. Here where we said sine was y over r, cosine was x over r, tangent is y over x. If y is sine and x is cosine, then tangent is sine over cosine. So we can divide the y value by the x value to get the tangent. That being said, coming back up here, where we have like 45 degrees, x and y are the same values. Dividing those out, you get 1. If we come down to our triangle, tangent is opposite over adjacent. 1 over 1 is 1. And sure enough, it works out rather well. So we can get those function values rather easily, actually. All right, now we're going to jump over to actually looking at the graphs of sine and cosine, as well as tangent. But let's take a quick look at the values we have here. I'm going to look at sine. As we rotate around the circle, what happens to the sine values? We start at 0, go to a half, root 2 over 2. Now remember, root 2 is about 1.4, so divide that by 2 is about 0.7. Root 3 over 2, that's about 0.86, up to 1. And then we work our way back down to 0, and then we drop below 0, kind of at the same rate, until we get to -1, and then we start working our way back up to 0. So those y values start at 0, up to 1, back to 0, to -1, back to 0, up to 1, back to 0, -1. And you can see this will keep going forever unless I stop. And you probably wished I stopped a little while ago. But let's take a look at that and see how that looks on a graph. I've brought up Desmos, which is really handy, I think. Y equals the sine of x. And sure enough, we start here at 0, and we work our way up to 1, back to 0, back to -1, and I'm just looking at the y values. 0, 1, and so on. Now the x values would be the angles. There's pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, and so on. And so this would be what sine looks like. Now if I take a screenshot of that so that we can talk about some of the features associated with it, then perhaps that will allow me to highlight some features on the graph. Make it big enough we can actually see it, use it. All right, get rid of some distraction here. And there we have the graph of sine. We just did y equals sine of x. I'm going to put sine of theta. And this is clearly in radians because it only went to 2 pi, which 2 times 3.14, so about 6.28. All right, now they call this distance the amplitude. It is the half the distance from the trough to the peak. Now I say it that way instead of the distance from the x value, because later we're going to move these graphs up and down. And so recognizing half the distance, I think, will help us when it moves away from the x-axis. That's our amplitude, and notice I said this keeps going, so we call this a periodic function because it keeps going through the same segments over and over again. And the period is the distance from where you start your motion until it starts to repeat. So in this case, the period is 2 pi. Our amplitude in this case is 1. When we use a very basic function, that's our amplitude. How high does it go? The period, how long does it take, or how large is the angle through which you have to turn before you get back to where you started? That was 2 pi, I'm sorry. So now we know the amplitude and we know the period. We can also see that the range of this function, since we've often talked about domain and range, the range is from, oh, I should use a bracket because we actually include it, -1 to +1. That's the range of the sine function. The domain are the x values, and it's everywhere. So the domain of sine is -infinity to infinity. That gives us our domain and range of this particular function. Now we know the amplitude, we know the period. There's one more thing that we talked about in algebra that we need to look at here, and we'll just use pi over 2 as an example. Sine of pi over 2, and we already saw this before, equals 1. The sine of -pi over 2, I'm going to put that in parentheses so we don't confuse the negative with a minus sign, is -1. And remember, when we said that f of x equals, f of -x equals negative f of x, it was an odd function. We also said when f of x equals f of -x, it's an even function. And this tells us that sine is an odd function because f of -x, so if x was pi over 2, and we negate that, make it -pi over 2, what did we end up with? We ended up with the negative version of what we started with. And so when you negate the x and end up with a negative version of what you started with, it's an odd function. Let's take a look at cosine. That was sine. Let's take a look at cosine. It looks like it's been shifted just a little bit, but it's actually a little different. This would be looking at the x values in the unit circle instead of the y values. Let's add some of that. Actually, that might be good to keep. So now we can see the f of x and so on. Okay, so now we're looking at not cosine, but not sine, but cosine. Notice, where do we duplicate? So if we start here and go to there, that's our period. That's where it starts to duplicate. Again, that's 2 pi. Our amplitude, we could go from the middle to the peak or the trough. Amplitude is again 1. But let's see, we started where our x value was 1. Cosine of 0 degrees is 1. So that's the big difference between sine and cosine. Sine started here at 0 and went up. Cosine starts at 1 and drops down. We still have to get through 2 pi to get there. Now let's look at some values here. Let's look at pi. So the cosine of pi is -1. Let's look at the cosine of negative pi. Cosine of negative pi is also -1. So now we're in this case here where f of x, f of positive pi, equals f of negative pi. We got the same y value. So cosine is an even function. Sine is an odd function. The domain, stop pushing that button. The domain is, again, -infinity to infinity. The range is, again, -1 to 1. We're going to use those later. That's going to be important for us. Let's go back to Desmos real quick. Let's look at tangent. Tangent's an odd one. Actually, I'm going to come back here to my unit circle. Let's look at tangent. We started, tangent is y over x. So we would start here. Y over x is 0 and work our way up to undefined. Back to 0, undefined. Oh, that's kind of odd. So let's go back to Desmos. We've got some undefined in there. That's going to give us a vertical asymptote. And sure enough, it does. Tangent's kind of weird this way, but notice that at pi over 2, it's undefined. At 3 pi over 2, it's undefined. And so now our domain is everything but pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, or any pi over 2 plus any multiple of pi. So that changes our domain. Our range here is all real numbers. So that becomes a little different. Just for fun, here's the sine function. What's the inverse of sine? You'll recall from last week, 1 over sine is cosecant. So if we take the inverse of, or see what cosecant would look like, that's going to be odd. Not even odd, but it's going to be weird. Because we need to take 1 over the y values we have here. 1 over 0 is undefined. So everywhere sine crosses the x-axis, we're going to get undefined. 1 divided by 1 is 1. So up here at pi over 2, we are going to have that same spot. Over here at 3 pi over 2, 1 divided by -1 is -1. We'll be in the same spot. Let's take a look. What is cosecant? Just like you thought, asymptotes everywhere sine crossed the x-axis. It's going to hit where y equals 1 or -1, but everything else, remember, 1 over a very small number, like right here, is a very large number, and that's why it's going away in this fashion. Bring up cosine. 1 over cosine is secant. It would be pretty similar. Cotangent, again, 1 over tangent is cotangent. So everywhere tangent crosses the x-axis becomes an asymptote. Where it's up at 1, that'll be the same place. That's 1. Looks like it's flipped. And if you turn these all on, it looks kind of like art. But just kind of gives us a sense for what those graphs look like. Later, we'll play with those graphs a bit more. But for now, we need to get a sense for what. Matter of fact, let's look at some transformations of those graphs, which is section 6.6. You know this video is getting long, but hopefully it'll work and you can bear with me okay. All right. So remember in algebra, we talked about transformations and we added these variables A, B, C, and D. Well, those modified our functions. We had vertical translations, we had horizontal translations, we had vertical stretch and shrink, we had horizontal stretch and shrink, and we find the same thing exists with these transformations. Only now, because it's a periodic function, it's going to look a little different. So I'm going to go ahead and type it just the way we had it there. Y equals A times the sine of bx. I think, let me go back. Was it plus c minus c, bx minus c, and then we added d to it. Minus c, oh, put that inside, and then we added d. Okay, so I'm going to add some sliders here so that we can see what happens. Now, I am going to drop d down to 0. Well, I'm kind of giving away the deal, aren't I? I know I use sine, but cosine would be the same. D was our vertical translation. So if we have a negative d, it's going to drop it. If we have a positive d, it's going to raise it up. If it's 0, then there is no vertical translation, and it is right on the x-axis like we started with. So what would C do? Now, you'll recall from algebra, if we add or subtract inside the function, that's a horizontal translation. So let's kind of move C, and you can see that sure enough, we get a horizontal translation. If C is 0, there is none. So this is our original sine function with no translations. A, that's outside the function, so that affects it vertically. It's multiplied, so that would be a stretch or a shrink. So A is going to affect our amplitude. If we go above 1, it's going to increase. If we go below 1, it will decrease until this thing gets pretty flat. Now, a negative is a reflection about the x-axis. So if I do -1, that is a reflection about the x-axis of our original sine function. Just take it and all the values flipped. Take it back to +1, so we're multiplying by 1, and we're back to our original function. B is inside the function. When you multiply inside the function, it is a horizontal stretch or shrink. So if we multiply x by 2, now we've changed, let's see, it's coming closer together, so that's affecting our period. Period of the function changes as b increases. As b decreases, again, the period changes, only it elongates. So it's like a horizontal stretch. If the number gets bigger, it's a horizontal shrink, just like we saw in algebra. So all of that becomes really useful for us, only now we need to describe some terms associated with that. So what I'm going to do is I'm going to show you a little bit. We've already shown that B is a horizontal stretch or shrink. Now they've taken the absolute value of B, because if it was negative, now we have a reflection about the y-axis, but we're not going to deal with that. We're only going to deal right now with the stretch shrink portion. If it's less than 1, we stretched it. If it's greater than 1, we shrunk it. We saw that on Desmos just now. If it's less than 0, it reflects. So that's going to affect the period. Now notice they say the period is 2 pi divided by b. So let's go back here to Desmos. We're going to change b to 2. What is the period? We've gone, I'm going to show our original function where the period was 2 pi. Notice now we get through one full section of the graph in 1 pi distance. So if you take 2 pi and divide it by the b value, which is now 2, you get the new period, which is p. pi. I'm sorry, pi. So dividing 2 pi by the b value gives you the new period. So if we took this up to 3, 2 pi divided by 3 would give us the period. So we come up here and it would be right there, which is 2 pi divided by 3, just like we expect and just like we saw. Take this back to 1, so we're back to where we started. By the way, this figure or this table that I'm looking at here is on page 470 in your book. You can always refer back to it. Let's take a look at a different variable. We'll look at A. A, we said, affected our amplitude. It affected our vertical stretch and shrink. If A is less than 1, we get a shrink. If it's greater than 1, we get a stretch. If it's less than 0, we get a reflection about the x-axis, and we already saw that with the sliders and decimals. The amplitude is the absolute value of A. Remember, the amplitude is the distance from the midpoint up to the graph. And again, if I translate this up, you can see that the amplitude is no longer the distance from the x-axis. It's half the distance from the peak to the trough. So here it's 1.2, that's 3.2. The difference between those two is 2. Divide that by 1 is 1. So the amplitude is still 1, even though we've moved this thing up away from the x-axis. So the amplitude is A. And I'm getting too crazy, I guess. A here is 1, and we saw that. Our amplitude is 1. Amplitude is A. Keep going. Translations. We had vertical and horizontal translations. The horizontal translation was our C value. But notice they have C over B is that horizontal translation. They call that a phase shift. And you notice that a lot in sound. If you've got a speaker that's close to you and a speaker that's further away, and they're playing the exact same music at the exact same time, the sound from the closer speaker will hit you first, and the sound from the further speaker will hit you second, and it will sound like it is delayed. That's phase shift. It is out of phase with the closer one. So in a movie theater, they do their best to get the speakers in such a way that everybody gets virtually no phase shift. But if you've watched Big Bang Theory, you know that Sheldon keeps going around until he finds the spot where there is absolutely no phase shift, the prime spot. Now let's look at this, why it's C over B. So we're really only talking about B. If I move this thing up to 2, I'm sorry, we were talking about C. If I leave that at 1 and move C, all I'm doing is sliding this thing over, right? But what if B isn't 1? What if B is 2? Now what happened to our phase shift? Where C was originally 0, there was no phase shift. All we had was a horizontal stretch or shrink. But now let's look at where we're crossing 0 at 0 right now. If I move this up to 1, where do we cross 0? We didn't move over 1, we moved over a half. And so that's why it's C over B. That change in our period affects the phase shift. And you don't notice it until both B and C are changed. But when they are, it's very clear that you need to include both of those. Again, I'll come back to this slider, and I'm looking at C, which is the phase shift. And I went from 0 up to 1. I really only moved on the x-axis over 1/2. And that's because B was not. So keep that in mind. Your phase shift is C over B. And now our vertical translation is just B, whether that moves you up or down. And we saw that already over here in our sliders. We can move up or down a distance D from the x-axis. That one's pretty straightforward. It's the phase shift that's odd, that's C over B, and the period is 2 pi over B. Other than that, this follows the same sort of translations that we saw in algebra. So you can feel pretty comfortable with that. And again, this table is in your book on page 470. So that gives us a sense and kind of wraps up our discussion of chapter 6. That's our intro to trig. We've talked about degrees and radians. We populated the unit circle, and that was really helpful for us because now we can get the sine, cosine, oh, that's not new. We can get the sine, cosine, and therefore tangent of any angle that's on this unit circle. Oh man, that's a mess. Hopefully you can still read it well, or you can back up the video, but that will help us to understand sine and cosine of all of these angles, and we'll use that later on. If you've got questions, let me know. Hopefully that was a good help and you feel comfortable with chapter 6. Remember, we're testing next week. I guess I shouldn't say that since I'm going to use this video for later classes. But again, if you do have questions, feel free to reach out.